Yeah, hello, I'm Shuhei Ikemoto, an associate professor in Kyushu Institute of Technology. I'm really happy to have an opportunity to talk in this nice workshop. So at first, I'd like to convey my thanks to organizers for making this workshop to be placed in this very difficult situation. So thank you very much. So in this presentation, I'm going to explain about the new method to give tactile sensing capability to inflatable robots. Sorry. Okay, as shown in this slide, a variety of inflatable robots have been developed since the beginning of the 2010s, and they have been the subject of a wide range of research from fabrication methods to control methods. Also, there are some differences in the driving and control methods of joints, but these robots have one thing in common in that their rings are composed of balloons that are inflated by compressed air, which is very natural since they are inflatable robots. So there are three main reasons to use an inflatable link. It is extremely inexpensive, extremely light, and soft. Because they are all features that facilitate contact with the environment, many inflatable robots are intended for actively contacting the environment, which is difficult for normal robots to do. Therefore, tactile sensors are considered to be a high priority sensor for installation, but it is difficult to install existing tactile sensors while maintaining their features. In fact, these robots are not equipped with tactile sensors. So in this research, I'm trying to propose a tactile sensing specialized for inflatable robots. For this purpose, I think that several requirements need to be met. The first point is that to keep the cost inexpensive, the sensing device should be common and cheap. And the second one is to make the fabrication easy. The sensing device should be easy to install in the fabrication process. In order to satisfy these 2 points and to keep the link soft and light, the material of membrane should be able to be selected independently of the sensing, I think. So this is the third point. In order to satisfy these 3 points, I'd like to make use of the characteristics of the inflatable robot, which is composed of balloons. So because measuring internal pressure of balloon can be done from the distance from the point of contact, this would be convenient to meet these requirements. So at first, let me use a very simplistic example to illustrate the fundamental idea of the proposed method. Now, we assume a thin and soft tube as the simplified inflatable link. If pressure sensor is attached here and the other end is closed like this, the deformation of the tube due to contact can be observed as a change in pressure. In this case, it would be possible to know that a touch was happened. However, the position of the contact cannot be known. A simple approach to locating the contact point would be to divide the tube into several parts and attach a pressure sensor to each of them. In this case, the contact position can be determined by which pressure sensor the pressure increase is observed. However, the more you want to know the contact position, the more you have to separate the tubes and install many pressure sensors. This should be troublesome and imposes a design constraint on inflatable links. Also, the robot becomes ugly. Therefore, I'd like to consider the following method. The first, I do not do anything to the tube, but just attach pressure sensors to both ends of it. In this case, the two sensors look like they measure the same pressure change caused by the contact. However, even though the pressure change is very fast, there is some amount of delay in its propagation as much as the sound. So there is a difference in the time that the pressure change reaches to the two pressure sensors. In this case, if we know the velocity of sound in the tube, the position can be easily estimated by multiplying the sound velocity and this difference of the arrival time. It's called TDOA feature. The validity of this concept has already been confirmed in the very simplistic experimental setup, and this research is already presented in the paper below. So in this research, I'd like to consider extending this method to a balloon which constitutes an inflatable robot. Assuming that now we attach n pressure sensors to the same balloon, and because one TDOA feature can be taken from 2 pressure sensors, the number of the 2 combination of them is the number of TDOA features what we can take. Each TDOA feature is theoretically expressed by the velocity of sound in the balloon and the difference of the distance to the contact point from the 2 sensors. So we can write that TDOA feature like this. And we can formulate the squared error function that we should minimize for estimating the contact point like this. But actually, what we want to know now is the position of the contact happened on the balloon. So there actually should be the equally constraint. That means the implicit function expressing the surface of the balloon. Considering the shape of inflatable balloon is very difficult to know in advance, so it is obvious that these parameters written in red color are very difficult to know in advance. On the other hand, gathering the data would not be very difficult in practice. Specifically, from here, let me assume that 4 pressure sensors are attached to the inflatable ring, I mean the same balloon. In this case, we can get 6 TDOA features from them. In order to correct the data, it is only required to contact a predetermined position and measuring its TDOA features and repeat this process. So these pairs of contact position and TDOA feature vectors can be used as a data set for creating a mapping between them. So to create the mapping, of course, we can use a machine learning technique for it. In particular, in this research, I used random forest for both classification and regression because it has fewer hyperparameters and it is easy to use. Okay, in order to validate this method, I prepared a simple experimental setup. The center picture shows the overview. This is composed from a cylindrical seat and 2 parts to close the end of the cylindrical seat. Each end part shown in the left pictures has a port for pressurizing the inside of the balloon and 2 pressure sensors. About the cylindrical seat, the 4 black tapes, which is the vertical one, are put on the surface of the balloon to show lines that equally divide the circumference, and red, yellow, green, and blue tapes are put to show the lines that divide the longitudinal direction, the horizontal one, as shown in the right figure. Okay, in order to collect data, I hit 16 intersections of tapes by finger. So at this moment, time series of 4 pressure sensors were recorded at 50 kilohertz for 1 second. But unfortunately, the selection of the pressure sensor might be not good. The data was very noisy, as shown in the center graph. So I applied a moving average of 100 points and remove the high frequency component. So to take TDOA features from these filtered time series data, I used cross-correlation function of each 2 combination of them and computed the TDOA features as values of the lag that maximize the cross-correlation functions. I repeat this process 30 times for all intersections So, 480 data points were obtained in total as the data set. If each of 4 black tapes is numbered 1 through 4, and the colored tape are also labeled R, G, B, and Y respectively, then all intersections can be called by these labels, as shown in the top row of this matrix. Because intersections of tapes can be used as the labels, at first I created a classifier from the dataset by using random forest. For the training, randomly selected 360 points were used, which is the 75% of the dataset, and the remainings were used for the validation. So this matrix is the confusion matrix of the result. As you can see, almost outputs of classifier were counted into the diagonal elements, and only few were counted into non-diagonal elements. That means misclassified. So in summary, the accuracy rate is about 93% here. So this result indicates that the TDOA feature is a kind of good feature to estimate the contact position, and the approach is thought to be valid. Okay, by using the same data set, I trained a regressor using random forest as well. For the training, labels using the classification are converted into 2D position vectors of corresponding intersections that consist of the longitudinal coordinate and the circumferential coordinate. As the result of training, the random forest regressor was fit with 0.88 R-squared determination coefficient score, which means the training was sufficiently achieved. The estimated contact positions for the validation data is shown in this figure. Since the contact position is just a conversion of the label of each intersection, unfortunately, the variation in the same intersection is not taken into account in this data set. Therefore, also the estimated contact position in this figure appear to be very scattered. The fact that the estimator was trained with high determination coefficient means that the regressions can be expected to be highly accurate if we use a data set that directly measures the contact position. Okay, to address this point, I have confirmed that use of a motion capture system would be suitable for this purpose. So these movies show captured motions interacting with an inflatable link. As shown in these videos, the positions and posture of the inflatable link and the movement of each finger touching it can be measured simultaneously in detail. So therefore, I think it would be possible to collect a large amount of data for learning by preparing this kind of measurement environment. And considering the use of such a measurement environment, it would be better to develop and use an entire inflatable robot instead of using a single inflatable link. Therefore, now we have started to develop an inflatable robot with full body tactile sensation. But unfortunately, our progress has been slow due to COVID-19, but we hope to have a prototype by the end of this year. In this presentation, we measured a single point contact, but I think if we use the information of the magnitude of the pressure, we can also estimate its intensity. However, if we try to measure the contact position and strength of multiple points, we need to install many pressure sensors, and learning the classifier and regressor must become much more difficult. Therefore, it may make more sense to take higher labels such as stroking, tapping, grasping, and pinching, and so on, and have the inflatable robot recognize where that kind of event was happened. The result of this study can continue to be used in this kind of future work, in the sense that the spatial information of where appears in the TDOI features in this case. Okay, that's all. Thank you for listening.
Thank you very much, Shuhei. Very exciting. So it's not only unconventional sensing, but also the whole embodiment and control as well. It's a very exciting work, and I think it's like the whole new field for applying algorithms for detecting gestures and so on when you interact with these robots. Is there any quick question? We don't see any on our channels. I will maybe ask one quick one. So how well would this approach kind of scale down? So if you have your inflatable fingers, for instance, right, so much smaller tubes, can you still apply this in principle? What would be the challenge?
I think if the balloon was very small, of course, it is very difficult to apply this kind of method to such kind of small balloons. But in this study, I used the sampling frequency was only 50 kilohertz, but actually, so it comes from the bottleneck from the AD conversion of my device. But actually, I can get some commercialized AD conversion device which has few megahertz sampling. So I think I can make more efficient on the experimental setup. So I'm not so sure whether or not we can apply this method to very small balloon like finger, but yeah, anyway, I can improve the resolution of spatial resolution of this method in the future, I think.
Yeah, thank you. Okay, thanks again for your presentation. So I have virtual applause.